Okay, so let's continue the material in section 6.1. We still have one more example. Yeah, I show you one more example, and then we will finish section 6.1 and talk about section 6.3. And after that, we will talk about section 6.2. Come back to section 6.2. Section 6.1 and the section 6.3, they are related. Yeah, and section 6.2 you could view as an application. So we taught this section 6.2 in the end. Okay, yeah, and after that we finish all the material you should prepare in your final exam. Yeah, and if we still have time, we could talk more, but it's not in the scope of your final exam. Anyway, so let's see. So we consider 3x3 case. And again, we want to find its eigenvalue and eigenspace. Actually, we want to find the eigenvector. But as we say, if we want to know the eigenvector, then of course you should. For the eigenvalue, it becomes a space. So actually, you could choose any vector in its eigenspace. Non-zero vector in its eigenspace, then it's the eigenvector of A. Okay, so let's see how to solve it. So as we say first step, just consider determinant A subtrate lambda I. And it's exactly determinant is a notation. And A subtrate lambda I means that for the matrix, subtrate lambda I here is 3x3 matrix. So lambda I is lambda. It's this one. So A subtrate lambda just in diagonal entry we should subtrate lambda. In diagonal entry we should subtrate lambda. This one subtrate lambda. And for another one, just for another entries, just keep it this one. So it's determinant this one, and it's determinant. Then for this case, you could see that we have 1 0 row. No, I mean in the third row it's 0 0. So we could expand along this row, right? So if we say is positive, negative, positive. So we expand along this row. So it's 0 times 0 0. So we just need to focus on this one. 2 subtrate lambda times delete this row, this column. So we still have 1 subtrate lambda, 1 0, 2 subtrate lambda. This one. So it's exactly 2 subtrate lambda and multiplied by here is diagonal entry. No, not diagonal. I mean it's 1 subtrate lambda times 2 subtrate lambda. Divide subtract 1 times 0 is 0. This one. And it's exactly 2 subtrate lambda, 1 subtrate lambda, 2 subtrate lambda. So it's this one. This one. And actually you could see when you do the determinant of this matrix, you could see it's upper triangular matrix, right? So as we say in chapter 2.1, if it's upper triangular matrix, its determinant is exactly this one. The product of the diagonal entry, right? So actually you could do it directly in this way. And of course you also could expand by this column, and you could get a same solution. Anyway, so it's determined this one. And our first step is to figure out its root. Determinant A subtrate lambda equals 0. This equation is root. Okay, so we should find its root. So what's the root? This one, so you could see that if we let determinant A subtrate lambda I equals 0, then its root equals 1 and 2. So as you see, it has 2 eigenvalues, 1 and 2. But for the eigenvalue 2, it happened twice. It had multiple roots. It had multiple repeat roots. Okay, 2 is a repeat root. Okay, so second step, we have 2 eigenvalues, so we could denote by lambda 1, lambda 2. So for lambda 1 equals 1, then what can we say? if eigenvalue is 1 and 2, but we should figure out the eigenspace or eigenvector. So you should check A substrate lambda I is x equals 0 is solution set. A substrate lambda I x equals 0 is solution set. So A substrate lambda 1I is exactly, here is A substrate lambda 1 is 1. So as we say, what does it mean? It means that for the matrix, in its diagonal, we should subtract lambda 1. In its diagonal, we should subtract lambda 1. So it's 1 subtract 1, 2 subtract 1, 2 subtract 1. And for another entry, just keep it. Just keep it, this one. And it's exactly equal to 0, 1, 0, 0, 1, 0, 0, 0, 1. It's exactly this one. It's exactly this one. And then now we want to figure out this matrix is its null space. Its null space means that its solution set 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. It's solution set. And so for its solution set, just we could cancel one row, right? So you could get 0, 1, 0, 0, 0, 0, 0, 0, 0, 1. Right? So we denote it by the variable s1, s2, s3. So what can we say? We can get two equations. S2 equals 0 and S3 equals 0. Right? So you could get these two equations. So what's the solution set of A substrate lambda 1 and 0? Or you could say null space of A substrate I lambda equals 1. And it's the eigenspace of A, corresponding to eigenvalue 1, corresponding to eigenvalue 1. And it's the solution, so it's S1 is any, if we have no restriction for its solution set, for the variable S1, we don't have any restriction. It means that S1 belongs to any real number. And S2 should be 0, S3 should be 0. So no restriction means that S1 could be any real number. S1 could be any real number. And actually it's the span set of 1, 0, 0. It's the span set of 1, 0, 0. This one. This one. Okay, so it's the eigenspace of A corresponding to eigenvalue 1. And next one is the case when eigenvalue equals 2. When eigenvalue equals to A subtrate lambda 2I, it becomes in diagonal entry we subtract 2. So diagonal entry we subtract 2. So it's 1 subtract 2, 2 subtract 2, 2 subtract 2, 1, 0, 0, 0, 0, 0. So it's negative 1, 0, 0, 1, 0, 0, 0, 0, 0. This one. This one. And again, consider A 0, so it's 0. So it's no. So it's negative 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This matrix is null space, means this AX equals 0 is solution set. And it means S1, S2, S3. So what does it mean? It means that for its solution set, it satisfies this equation. Negative S1 plus S2 equals 0. And what does it mean? It means S2 equals S1. And what's the solution set? So it's null space. It's null space of A subtract 2I. It's equal to here S1 equals S2 and S3 will have no restriction. It means that S3 could be any real number. Otherwise, you also could say, you could, of course, S3 is the free variable, and you could let S2 be free variable. Then S1 equals S2, right? Okay, so S1, S2 is equal to S1. So here is here. Let S1, of course, you also could let S1 be free variable, then it becomes S2 equals S1, yeah. If you just want to know just want to write down its solution set, you could label it by S1 or S2. That's fine, it's just a scalar, it's just a scalar. Anyway, so S3 could be any real number, so you could write this. And here S1, S3 is any real number. And for this one, you could rewrite it by this way. It's x1, s1, 0 plus 0, 0, s3. s1, s3 is any real number, But what's this? Here it means that it's x1 times 1, 1, 0. And here it means that s3 times 0, 0, 1. 0, 0, 1. So finally it's the space of 1, 1, 0. And here is 0, 0, 1. 1, 1, 0, 0, 0, 1. So this one is space of 1, 0, 0. And this one is 1, 1, 0, 0, 0, 1. This one. So of course if you choose this one is eigenvector, but once you multiply any non-zero scalar, it's also an eigenvector corresponding to 1, corresponding to eigenvalue 1. Okay? Yeah, it's the last example. Okay, so now just tell you some notes. In the previous argument, I could tell you some notes, and then we finish this section. Just tell you some notes. If A is an n by n matrix, then what can we say? Determinant A subject lambda I equals 0. If we have n by n matrix, for example 1, 2, 3, 4, and we consider if we want to figure out its eigenvalue, then what does it mean? Consider determinant A subject lambda I equals 0, and to figure out its root, to find its root. And what does it mean, A subject lambda I? It means that for the matrix A, in the diagonal entry, we should subtract lambda, and consider its determinant. And once you consider its determinant, even it's not in 2 by 2, probably it's this one, 1, 2, 3, until n, and something else. And subtract lambda, then consider its determinant, you will see, it will contain at most degree n, the power lambda, at most we have the power n. So for its equation, for this equation, the variable x lambda and its power at most it could be n. And actually we have the 10 lambda to the power of n. Lambda to the power of n, this 10. Actually we have this 10. When you consider that its determinant, we have this 10. Yeah, so actually it contains it must have n roots. So determinant A subject lambda I equals 0, it has n roots. And of course here it could be repeat. For the roots it could be repeat. For example 1, 2. And here for the eigenvalue 2, we have the repeat. The eigenvalue 2 is repeat, right? It's repeat. Okay, so it has n roots. But for its eigenvalue, it could be complex, not just real. It could be complex. Just in some matrix, sometimes, let me give you an example. For example, 0, 0, 1, 1. Then determinant A subject lambda I. What's this? Let me see. 1, -1, this one. Okay, for example, this one. What is its determinant? What is its eigenvalue? When you consider A subject lambda I, its determinant. Then it becomes determinant A subject lambda. So for the diagonal entry, we should subtract lambda. And what's the determinant? Negative lambda is square subtract 1 times -1. So it becomes lambda squared plus 1. Right? So it becomes lambda squared plus 1. But for this equation, if relay be 0, then what can you get? Lambda equals positive, negative I is the imaginary number, right? So it could be complex number. Not always real number. But it will exactly contains two roots. Okay. The second one, if A is upper triangular, if of the form upper triangular, what can we say about its eigenvalue? What can we say about its eigenvalue? As we know, if we want to know its eigenvalue, you should consider this one. But once you consider this one, it means that for the diagonal entry, we subtract lambda, and consider its determinant means that determinant A subtract lambda I equals just becomes lambda 1 subtract lambda 2 subtract lambda until lambda n subtract lambda. This one. So when you let it be 0, what can you get? Lambda equals lambda 1, lambda 2 until lambda n. So it means that all of them are the eigenvalue of A in its diagonal entry. All of the values are the diagonal entry. All of the diagonal entry are the eigenvalues of A. All the diagonal entries are the eigenvalues of A. The last one. And for the last one, before I tell you the last one, I should tell you the notation, the definition about the name. Because in next section, section 6.3, we will use this one. Actually, it's the definition in section 4.3, but for this section we skip it. But for the name, you should know that. If we have two matrices, AB are n by n matrices. If we have two matrices, and if we say A and B, these two matrices are similar. They are similar. What does it mean? It means that if we say two matrices are similar, it means that they have this. It means that there exists some invertible matrix. Invertible P matrix P is also n by n matrix. There exists invertible matrix P such that it's an important concept. B equals P inverse AP. It's an important concept. In next section, section 6.3, we will focus on this part. We will talk about similarity. Similar is an important concept. Similar. It means that we could find some invertible matrix P such that B equals P inverse AP. Okay, maybe, yeah, it's the same. B equals P AP inverse. But as we say, originally I just write down in this way. But if you let Q be P inverse, if you define Q by its inverse, then then you could see that P equals Q inverse and B becomes Q inverse AQ, right? Then it becomes this one. So I mean for this invertible matrix P, you could write it this way, PA P inverse, or you could write it this way, Q inverse AQ. That's fine. Okay, that's fine. So as we say, two matrices A and B, they are similar. What does it mean? It means that we could find an invertible matrix P such that B equals PA P inverse. And the two matrices are similar. It's an important concept, and they have nice result. What's the nice result? So that's why we introduce it here. What's the nice result? Let's see the third one. If two matrices AB, if AB are n by n matrices, A and B, AB are n by n matrices, and then you will say A is similar to B. Then A is similar to B. Then what can we say? A is similar to B means that we have this result, this one. Just follow the definition. And with this definition, what can we say? they have the same characteristic polynomial. I mean, if you consider its determinant b, let me see. If you consider determinant, okay, now we want to know. Actually, our goal is to show they have the same eigenvalue. If A and B are similar, then I want to tell you they have the same eigenvalue. So it means that we should consider the determinant A subject lambda I. So let's see what's their difference. A subject lambda I and B subject lambda I, what's their difference? And we will use this equation to show them. So we will use this equation. So we start from this one. We start from this 10. So B subject lambda I. How can we rewrite this 10? How can we rewrite this 10? B is this guy, P, A, P inverse. B is this guy, right? B is this guy. And the subject lambda I, we could rewrite it by this way. Identity, the matrix, identity matrix. What's the identity matrix? Identity matrix in diagonal entries is 1, otherwise it's 0. Otherwise it's 0. So you could write it this way. Actually it's a trick. I mean, we could write it this way. Identity means identity equals P times P inverse. Any matrix multiplied by its inverse equals identity. And here for this part, we also could rewrite it by this way. For this 10, it's equal to it's scalar. So we could let the invertible matrix P in the left-hand side. I mean P times lambda I times P inverse. For this matrix, we could rewrite it by this way. So now what's their subtraction? Now for the first 10, all of them are P, so we could keep it. All of them are P. And the second 10 is A. It's lambda I, so it's P times A subject lambda I. Just take out the common matrix P in the left hand side. And for the right hand side, the third 10, all of them are the P inverse, so put it in the right hand side here, this one. So now what can we say? B subject lambda I equals P times A subject lambda I times P inverse times P inverse. So what does it mean? It means that determinant B subject lambda I equals determinant P times A subject lambda I times P inverse. And for a determinant proposition, we know that we could separate. It's equal to determinant P times determinant A subject lambda I times determinant P inverse. We have the result, right? Determinant AB equals determinant A times determinant B. We have this result. So you could keep it, just consider this 10, then you could separate this 10, and for these two, for the product of these two matrices, you also could separate it again. So you could get this one. And actually here, maybe there is one way to show it directly. Determinant AB equals determinant BA. It will be simple to solve it. So for this 10P, we could put it in the right hand side. It's equal to determinant A subject lambda I times P inverse times P. This one. Since we know that determinant AB equals determinant, the reason is that all of them equals determinant A times determinant B. So of course we have this result. So we could put it in the right hand side, I mean it becomes here. So what can we say? Determinant here P inverse times P is exactly identity. And determinant any matrix times identity is exactly itself. So indeed we have this one. Determinant B subject lambda I equals determinant A subject lambda I. So what can we say? The result is that if A is similar to B, then we can see that determinant B subject lambda I equals determinant B subject lambda I equals determinant A subject lambda I. So in other words, if we let B 0, then it's equal to 0. And if we let B 0, then it's equal to 0. So So if lambda is an eigenvalue of B, means that this equation holds. Means that this equation holds. And it means that lambda is an eigenvalue of A. Okay? And for converse it's the same. So we can get eigenvalue of A. AB have the same eigenvalue. AB have same eigenvalue. AB, the two matrices A and B, they have the same eigenvalue. Actually, they have the same characteristic polynomial. Characteristic polynomial means this one. Okay. Yeah, but they don't have the same. They don't have the same eigenspace or eigenvector. They just have the same eigenvalue. Yeah. And it's important concept. In next section, section 6.3. And here for the homework, in section 6.1, we could check 1 A, B, C, G. Section 6.1, you could check by yourself. Okay, so all the results in section 6.1.